In this video, I am going to talk about another test for convergence or divergence called the integral test. So we're going to let g of x equal u of k, and we'll see what that kind of looks like in an example. So we're going to basically turn the series into a function and integrate that. So we're going to integrate if there's three conditions. G of x needs to be positive, it needs to be strictly decreasing, and continuous for x is greater than 1. If so, we're going to do the improper integral of g of x. If that one has a value and converges, then the series converges. If the integral diverges, then the series diverges. We use this test if our general term, our nth term, is easy to integrate. So let's look at an example. Okay, so we're going to use the integral test to determine the convergence of the harmonic series, which is the series from 1 to infinity of 1 over n. Now, in a previous video, we have talked about the harmonic series and have established that it does in fact diverge, but we're going to come to that same conclusion using the integral test. So in the integral test, we're going to take our nth term and write it as a function in terms of x. Okay, so my g is going to be 1 over x. It's really important to establish the three conditions. So the three conditions that must be met are the terms positive. Okay, for x is greater than 1, yes, they are positive. The second condition is the graph decreasing? Okay, couple of tools we can use. We understand that from this graph it's going to be decreasing. You can also use our handy dandy derivatives. If I take the derivative of 1 over x, you're going to get negative 1 over x squared. X squared is always going to be positive. That's going to make everything negative. So we can establish that this is always decreasing since the derivative is always negative. And third is this continuous. 1 over x is not continuous for all values, but it's only discontinuous at 0, and we're starting at 1, so we are good to go. It is continuous when x is greater than 1. So now we're going to use the integral test once we've established that the conditions are met. So we are going to take the integral from 1 to infinity of 1 over x dx. Okay. This is an improper integral. So what we need to do is use limits to make it a definite integral. So we replace the b with an infinity, and then we tack this limit on, and then it's going to be 1 over x. Then we integrate. Okay, integral of 1 over x is natural log of x, and we're going to be evaluating this from 1 to b. So we'll get natural log of b minus natural log of 1. Okay, natural log of 1 is 0. Okay, so that's going to go to 0, but the piece that's really going to dictate what happens is the limit as b goes to infinity of natural log of b. As b goes to infinity, natural log just continues to grow. So it's going to go to infinity. If that's the case, the integral diverges, which means the series diverges. Okay, our next example. We're evaluating this. Okay, these terms past 1 are definitely going to be positive. If the numbers as x goes to infinity, these are going to be bigger and bigger, so it is going to be decreasing. You can take the derivative if needed. Decreasing. And lastly, it is continuous because there's no 0 in the denominators. So it meets our three criteria, so we will use our integral test. So we're going to do the integral from 1 to infinity, and we're going to replace the n's with x's. Okay, now we said this, it should be easy to integrate. And on the surface, it could be a little tricky, but we can use our good friend u substitution. Okay, so I have x squared plus 1, which makes my du 2x dx. So we kind of have that. I'll go ahead and sneak my 2 in here, but that means I need to add a 1/2. Then I'm also going to deal with the limits of integration using limits. Okay, my 2x is now du. My x squared plus 1 is now my u. And we will integrate. So this will be 1/2 integral of this is going to be the natural log of u, evaluated from 1 to b. I did not change my limits of integration. You can if you want to, but I'm just going to go ahead and replace back in my original u. Okay, if you don't change the limits of integration, you need to replace this back in. If you do change the limits of integration, then you've already taken care of it here. That limit just keeps going along until we can establish what the limit's going to go to. Okay, so I plug in my b, I plug in my 1, which makes that 2, and we're interested in what happens as b goes to infinity. Well, as b goes to infinity, natural log of b, just like the last problem, is still going to infinity. So this one diverges. Okay, next problem. This guy is positive, this guy is decreasing, and continuous. Okay, I'm making a big deal about this because this is something that if this is on a free response, you must state that the 3 conditions have been met. Okay, so we'll do the integral from 1 to infinity of 1 over x squared plus 1. Well, x squared plus 1 is kind of one of those ones that's not always so obvious, but it is tangent inverse. So we're going to have tangent inverse of b minus tangent inverse of 1. Okay, tangent inverse pops up in these because tangent inverse is kind of a unique function in that it does in fact have a limit as we go to both negative and positive infinity. The graph looks something like this. So as I go to infinity, tangent inverse of infinity is pi over 2. And tangent inverse of 1 is pi over 4. That's where tangent equals 1. And you can calculate what this is. It's pi over 4. But really what we care about is that it is a finite value. If it is a finite value, then that means it converges. The integral converges, so the series converges. What's important to note, though, is the integral ended up being pi over 4. The series will not have a sum of pi over 4. So just keep that in mind. We don't actually know what the series converges to. We just know that it does, in fact, converge. Okay, next one. The series can look really interesting, but the thing is what we're looking for is, can I integrate this? And we can. This is positive. There's nothing that's going to make those negative. It is decreasing, and it is continuous greater than 1. So I'm going to evaluate the integral from 1 to infinity of e to the 1 over x squared. We are again going to use a u substitution. Typically we look for the composition and whatever the inside function's derivative is also a part. So my u is going to be 1 over x because du is negative 1 over x squared, which we kind of have. I need to make this negative, so I'll make this negative. Go ahead and make our improper integral into a proper integral by replacing the infinity with b. This is going to be u, and then the 1 over x squared is going to be du. So I end up with e to the u du, which is about as easy as those integrals can come. I'm also going to I'm going to integrate it, but I'm also going to, let's just go ahead and write this one more time. I'm going to make it negative, but I'm going to switch the limits of integration. As I said, easy integral, probably the easiest one we got. I am going to go ahead and replace back in my x. We could have done that with the limits, but in these I tend not to. So this is e to the 1 over x from 1 to b. So we're going to have e to the 1 over 1 minus e to the 1 over x. Okay, or 1 over b. Okay, so what we're looking for is b goes to infinity. If b goes to infinity, so e to the 1 is just going to be e. This is going to be e to the 1 over infinity is going to be 0. So this little piece goes to 0. So that's going to go to e. E to the 0 is going to be 1, which means my integral goes to e minus 1, which is a finite value, which means the series converges. Okay. Pretty common AP problem is to give you a bunch of series and determine which of them converge or diverge. This one's asking which ones converge. 1 over n. This one just has to be one you know, you see it, you know it is harmonic, which means it diverges. And the only justification necessary is that it's harmonic. Okay. These other two, these are pretty classic examples of where you're going to use the integral test. When you have natural log and 1 over n in your problem, that lends itself to the integral test. In the multiple choice, you don't have to be as clean with your notation. So you don't necessarily need to state in your multiple choice positive, continuous, and all of that. But okay, so this one is an easy one to integrate. Okay, I'm going to use a u substitution because I'm going to let u equal natural log of x because du is 1 over x. So this is u, the 1 over x dx is du, so this is going to be the integral from 1 to b of u du. If I integrate, we have 1/2 u squared. Substitute back in my natural log. Okay, the piece that we're interested in is what's going to happen to b. As b goes to infinity, natural log of b goes to infinity. So if we square it, it's still going to go to infinity, even if we cut it in half. So this one diverges. Okay, so back up here, this one diverges. So we have one more, which is pretty darn similar to the last one. So we'll use the integral test again. This one's going from 2. Okay, and we'll do this integral. I'm going to let u equal natural log again. du is 1 over x again. Okay, so my natural log is u, the 1 over x is du, so I get u squared. Just use our power rule. Okay, and then we'll go ahead and plug in infinity and 2. But you can probably already see where this is headed. Sorry, that should have been a B. I did that all the way. B's. B's. Okay, another parenthesis. So again, as b goes to infinity, natural log is going to go to infinity, so this also diverges. So we go back to here. So we got divergent, 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 so none of these converge. Always be careful to read whether they want divergent or convergent, and the amount of work shown is really up to you. But if you see natural log and 1 over n, those tend to be integral problems. So that was the integral test for convergence.